All right. So we're going to do another book review. Welcome back. This is Grob's Basic Electronics. Now, this is not just any electronic books. This is actually an electronic book that is used as a textbook for an engineering program. The specific engineering program is the one at Daytona State College. It's one that I'm a part of, and I'll be using this book in the electronics course. Now, the reason why I wanted to review this is because, well, one, if you're in that program or are thinking about joining an engineering program, then this will give you some insights into what the textbook is like. If you're also like me, you've also had some experience in certain areas of engineering, specifically electronics, and you might be curious about what the textbook is like and what the content is like. I definitely was. So actually, once I got into the program, I ordered basically all the books that I'll need for the whole program. So in pretty much every class I'm going to take, I've got at least 75, maybe 80% of the books, plus or minus some electives, right? Those might change, but all the kind of core classes that I know I'm taking, I have all the books already. And this is one I was particularly interested in seeing. And I think at the end, after we go through it, I'll give my kind of final thoughts. And maybe, actually I might just start now. For me, it's a little bit basic, but we'll go through it and see why. It doesn't mean that it's a bad book. Again, if you have some prior electrical knowledge, it might be pretty simple for you. So we'll zoom in here a little bit so we can see the table of contents. So we have a brief history and development of electronics, radio and television broadcasting, career opportunities in electronics, review or a preview of the most common electronic components, table of the trade or tools of the trade. Electricity. So this is just the first is just a preface, the survey of electronics, they're calling this, and then we're getting to chapter 1 here. So chapter 1, we have negative and positive polarities. Okay, electrons, protons, so we have some atoms and structures. That's typically how an electronics course will start, is going to start about atoms and positive and negative charges, potentially talking about conventional current. There might be some conversation about that in here. The structure of atoms, Coulomb's unit of electrical charge, the volt unit of potential difference, charge in motion is current, okay, resistance is the opposition of current, okay, the closed circuit, direction of current, AC and DC, sources of electricity. Then we get into types of resistors. So now we're getting into components, types of resistors, resistor color coding, variable resistors. I will say something about this. Let's see when this book was published. So this was copyrighted in 1997, but it looks like the first copy came out in 1959. So with that said, some of this stuff might be a little bit outdated. The reason why I mention that is because they're talking about the color coding of resistors, and not to say that the color coding of resistors is not a significant topic or one that you should know about. But since everything is moved closer to surface mounted devices, which are very small, which are implanted really with special tools, and they're not parts that we use by hand. The resistors aren't really color coded anymore. Most, at least service mount device resistors, like the ones you would find in an iPhone or in your cell phone and things of that nature. Now that electronics is at a smaller scale, that doesn't happen as often. But people like myself, for instance, will still use that stuff. That's all I use. I don't have any special surface mount device equipment. So I do everything on axle leads, point to point kind of thing. So moving forward, rheostats and potentiometers. That's important to know the difference. There's a lot of kind of physics in getting to understand the rheostats as opposed to potentiometers. Power ratings on resistors, series and parallel combinations. That's usually a big topic. You're getting to understand resistance networks. Then we have Ohm's law. So we have chapter 3 is dedicated to all of Ohm's law. So current, voltage, resistance, power formulas, open circuit and short circuit troubles. Then we have series circuits. Then it goes on. So we have a lot of topics in this book, at the least. We seem to have a lot of topics here. Let me zoom out a little bit here. So we're in series, and it goes to parallel on chapter 5. Then we have series and parallel. Okay. Then voltage dividers, current, direct current meters. So voltmeters, we're getting into a little bit of multimeter stuff here. Kirchhoff's law of current and voltage. Network theorems. Conductors and insulators. I would have probably liked to see that a little bit earlier. Conductors and insulators, I think, should probably go after electricity, maybe chapter 2. And then resistors, batteries. I do cover lithium cell batteries, so that's updated. Magnetism, magnetic units, electromagnetic induction. So we're going to talk about kind of inductors, Faraday's law, alternating voltage and current. What else are we going to get out of this thing? There seems to be, oh, even more. So there's a lot of chapters in here, which is nice, at least. Capacitance, capacitive reactance, capacitive circuits, inductance, inductive reactance. So inductive reactance, all this kind of stuff is going to likely go into impedance. RC and LR time constants. And the subject matter is good. Alternating current circuits. Complex numbers for AC circuits. Resonance. That's interesting that they have resonance in here. So resonance, so we're going to be talking about frequencies a little bit. Frequencies, and that goes right into filters. Cool. Electronic devices. Now we're getting into our semiconductors. PN junctions, PNP, NPN, field effect transistors, FET transistors. Testing diodes. I probably would have liked to see diodes come before. Well, if the PNP junction, okay, there it actually does. So with semiconductors, PNP junction, then it goes into semiconductor diodes, and then into semiconductor transistors. So that seems like that's a good sequence there. Electronic circuits. Okay, so now we get an analog, digital, amplifier gain, diode, rectifiers, transistor amplifiers. Chapter 30, probably going to be my favorite chapter there. That's what I've spent a lot of my time on in electronics, is amplifiers. So they talk about the classes of amplification. So A, B, C operation, analyzing common emitter amplifiers, which is the most common amplifier. FET amplifiers, trouble with amplifier circuits. You know, and amplifiers are very important because in any kind of electronic circuit, you'll find an amplifier for most anything. So let's go on to chapter 31, which is digital electronics. There's some Boolean algebra in here, which is cool. So you learn about some logic gates, hexadecimal numbers, flip-flop circuits. Those are interesting. Operations, so we get into integrated circuits a little bit. Operational amplifiers is the last topic. So let's flip through here. This is the survey, so it's just talking about some of the intro to electronics topics and the history. Now we're going to get into some of our components here. It has really good diagrams of, at least here, this is just the beginning, but it has some really good pictures of components. I just love looking at stuff like this. I'm kind of a collector in all kind of books, electronic books too. I like a lot. Electricity. Okay, this is where it's going to talk about the atom and its structure. Some talk of chemical elements. Voltage potential. How current differs from charge. That could be interesting. Like I said, it's very basic, but I would say probably a very good introduction for someone that doesn't have any prior knowledge. Okay. Conventional current, a very important topic. Now we're getting into resistors, types of resistors. Now it's getting to the color coding of resistors. Tolerance of resistors. Potentiometers, which is like or sometimes called a variable resistor. Ohm's law stuff. So this is just going to be some basic mathematics for Ohm's law. Nothing particularly tricky in there. Let's see if we can get into some more of the meat and potatoes over here of this thing. Conductors and insulators, that should be pretty basic. Like I said, it should have came in a little bit sooner. This is chapter 11. Of course, it's kind of self-explanatory what we're talking about there. We're talking about what conducts and what doesn't, and why. Let's see chapter 12. Batteries. That could be pretty interesting. Batteries is a big topic, you know. If I were to do it all over again, I always tell myself I probably would have not maybe got into battery technology so much. That's a little bit nearing the side of chemical engineering, but power supply design. Like power supply design has come a long way and is very interesting, and it's a lot of fun to really come up with really efficient power supply designs. And of course, every electronic piece of equipment needs a power supply. So I'm actually looking on the shelf next to me to see if I can find the book, and it's eluding me at the moment, but I have a little book here on switch mode power supplies, and that is the power supply that is kind of revolutionized electronics in many ways, and a lot of people might not know that, but it's something I've actually been wanting to make a video about for a long time, because its impact has been so great. Switch mode power supplies is why we have things at such a small scale now. That's why part of why electronics equipment has gotten so small is a large part due to the design of the switch mode power supply. So it's very interesting stuff. And what the switch mode power supply did, not to give it all away before I make the video, but what it did essentially is it took out the need for a large transformer. So we're basically taking what we used to do as a physical item with a large physical item, and we turn that into basically an electronic process. Okay. A transformer is basically it functions as we call it electronic component, but it basically functions as it's a function of physics, is how that works. It's not a function of electronics. It's a function of physics with the transformer. And this book doesn't talk about transformers, now that I come to mention it, which again kind of makes sense, because like I said, this is electronics. It's not about like power. Power would be more related to something that you would see with transformers. Magnetism. See, I think this should probably have came earlier. But we got some equations here for magnetism, which is kind of cool if we get into that. Again, let's get a little deeper. Let's see if I can get into the oh, look at this. Look at this. They're looking at ceramic disc capacitors, which are used a lot still. Now here are some surface mount, which is nice that they're putting this in here. They're putting some surface mount capacitors in here and trying to get you to read the codes off of them. Some picofarad stuff. Now we're getting into frequency. A very useful equation. That's the basic frequency equations here. Well, this one I believe they were actually, what were they doing? They were using the frequency. They were using frequency to calculate for the capacitance. Interesting. So that's a cool thing. That's a cool thing. So they're showing you how to reconfigure the equation. So let's say if you had a desired frequency, you can calculate what the capacitance would have to be. And we have some on paralleling, putting capacitors in series and parallel. RC networks. We're doing a little bit of trigonometry here, which is kind of cool, to calculate the impedance. Let's see if we can get into some of this amplifier stuff here. past it. I don't know. Let's see here. Wow, it's filters. It's got a block diagram. So power line filter unit, balanced line type, low pass filter. Interesting. So we get into a little power line filter. Oh, here we go with the junctions. This is going to be interesting. So like it's simple, but it's informative, which is kind of what I like about it. Electronic circuits. Now we're getting kind of into analog versus digital. This is going to be your analog. This is going to be digital here. Now we're getting a little bit into amplifiers. Modulators, diode rectifiers. Let's see, are we to an amplifier here? Analysis of the common emitter amplifier. Here we go. So of course this is in transistors. You know, most of my experience, a lot of, not one, I can't say, I guess I could say most, is in vacuum tube technology, but transistors are not too far apart. Transistors operate more on the function of current than voltage, which is where vacuum tubes operate. But here you go, you have a common emitter amplifier. Looks like kind of a stripped down version of a common emitter amplifier. Very few components. Showing you your 0.6 to get to the bias, the transistor. It's all about bias with transistors to get them to turn on. Gotta have a certain amount of voltage to get them to turn on in a certain place. Then we have our field effect transistor. And these are actually came integral. These are integral in, well, more IGBT, but field effect transistors are also integral in the evolution of the power supply. So very good to know about. So here's a more built out version of an amplifier. Okay, and it says troubleshooting analysis. Looks good to me. It looks like this should work, but you know, we'll get into this a little bit more maybe. I haven't done specific electronic videos in a while. I'll zoom in here so you can see it. That's your basic block diagram for a common emitter amplifier. You have a capacitor. The function of this capacitor oftentimes is to block the DC current that's at the gate of the transistor, not to go out into whatever is providing the signal. Okay, and then we have here is a voltage divider. That's your voltage divider there, and that'll give signal. That'll give a voltage to the base. I think I said grid earlier. The grid is vacuum tube. So this would be the base. The base. So that capacitor keeps the base voltage from going out into whatever's feeding the current on the other end. You know, so all this would be attached, right? So this is saying input signal, right? So that's gonna come from some kind of source, and then you have your 9 volts here, and then we have ground here, and then we have an output signal. So it's not labeled here because you're going to have to, you know, this is something that you'll just learn and memorize, that you have collector, base, emitter. Okay, and they call this a common emitter amplifier. Why? Because the emitter is grounded. Okay, so in a basic sense, kind of how this works is that a lot of your energy is going to come from the emitter, and it'll get pulled up to the collector, and that's where your output would go, and kind of layman's terms there. But here's your supply voltage. It goes into the voltage divider, which supplies the base. And you see here we have the 0.6 volt difference between the emitter and the base. That'll get our amplifier to turn on. And then we have a 1K resistor at the collector, and then another capacitor here, and that capacitor will keep that 5 volts from the collector from going out to the output signal. Now, these are all very important components. The capacitor here is not necessary. There's kind of a lot of, I guess, science that goes along with that that's pretty interesting in the operation of amplifiers. That's like basically it's kind of like an anti-feedback capacitor. So it lessens the feedback. And also, if you're doing audio stuff, you can also gain a lot of bass. You can gain a lot of bass and gain from changing the value of that capacitor. But here's kind of, along with that, this resistor here too is going to dictate a lot of what the voltage swing is, what we call this, is the voltage swing. So what happens here is this input signal is going to be very small. You know, it could be millivolts, and then it'll come out in volts on the other side. All right, so we have a small signal here, and then we have a big sine wave. This is what I'm doing with my finger here. So small sine wave, big sine wave kind of deal right here, right? So this resistor, that's going to be RE, because it's the resistor for the emitter. That's going to, along with RL, which is the resistor on the collector side, these two resistors are going to do most of the work, pretty much all of the work in dictating the amplification factor of this transistor. These two components are mostly for biasing, and it can all be tied together. Like you can say, obviously this does count as, this is partly responsible for biasing, but these are mainly responsible for biasing, and these two would be responsible for your amplification. And these two capacitors will be responsible for DC blockage. You can see they're at a high microfarad. That's likely because they don't want to have any frequency attenuation, which they will talk about in the frequency part. So this is kind of, and this is what makes it electronics interesting, but also just developing amplifiers interesting, because there's a lot at play here. So there's basically three things that you want to account for when you're building an amplifier, is like operating parameters and voltages, then frequencies, and then your amplification factors. Right, so all these things have to be balanced out, because depending on what you're doing, you know, let's say this wasn't for like audio. Let's say this was something, I don't know, audio digital, you know, so it was or analog to digital. It was analog to digital service, or it was something doing with radio frequencies or some kind of special signal that had to be preserved. Well, you would have to design this in such a way that none of the RC networks, because this is an RC network here, this is an RC network here, there's an RC network here, then there's an RC network here. None of these RC networks, an RC network is basically where a capacitor, which is C, and then the R is with the resistor, that network, that network is going to have a modulation factor when it comes to frequency, or potentially. Most common it will. You know, if you just slap two random capacitors and resistors together, there's likely going to be some frequency attenuation. So sometimes that's really important, sometimes it's not at all. A common way to avoid any is to put large capacitors, because then it almost doesn't matter what value your resistor is at. The capacitance rating is so high that it won't change the frequency. Oh, I had to restart my videos, going too long here, rambling about these amplifiers. But that's okay. So, integrated circuits. Integrated circuits are here. This is a block diagram showing you the inside of an integrated circuit. So an integrated circuit, it's just like, you know, what is a transistor? Well, a transistor is basically two diodes. That's how that's made. And then what is an integrated circuit? Well, an integrated circuit is a bunch of transistors and diodes and potentially resistors and capacitors that are just really small, all packed into one package like it's shown here. They're usually 8-leg, so the 4 on each side. This is a larger chip, but that's an integrated circuit. What most people, I think, would think of like as a microchip. Really, they're called integrated circuits, and they're just built out of really small electronic components like the ones we talked about earlier that are already prefigured to give you some kind of amplification factor, and they have a certain or function. It doesn't necessarily have to be, this would be an operational amplifier, so that's what we're talking about here. So what this does is it kind of just, it puts everything in a small package, and it gets to the point where you don't have to design all this, because some, you see here we have some like differential amplifiers and stuff, and looks, we have like a like emitter follower right here that goes into a collector follower and all this. You wouldn't need to do all of this. This is kind of like a, almost like a, you can look at this almost like a power amp section. Of course, it's not to that magnitude. It's just, it's the smaller magnitude. It's like a really powerful preamp, right? But that's basically what you're looking at here, and it'll have some prefigured pinout. Typical operational amplifiers will have a positive and negative voltage pinout. Here it's just showing you some equations about where you placed your resistor. So that's like a, what is this? A non-inverting setup. So you have the option with operational amplifiers, instead of, you know, with a resistor or with a transistor, you'll have to configure the schematic in a certain way in order for it to not invert the signal, or you have to invert it and then it gets reverted. But in an operational amplifier, they typically have 2 pinouts, so one for positive and one for negative, so you can choose based on the configuration of the circuit what kind of output you want. So if you don't want your output to flip-flop, then you can put it in a non-inverting side. Here's a summing amplifier. Unity gain, so this is pretty cool. You say, why do you want a unity gain amplifier? You know, this is kind of the stuff that kind of gets interesting and, you know, gets you thinking a little bit. So you say, this is a unity gain amplifier. So why do you have, it says unity gain amplifier, active low pass filter with the unity gain. But you'd say, in the low pass filter is where it would be, looks like it'd be here. Oh, that's actually this one. No, yeah, it would be, yeah, this is that one. That would be the high pass filter. We can go into Maybe I'll talk about that in a second. But you'd say, why would you want unity gain? Well, sometimes you use an amplifier not to amplify anything, but you use it as a way of changing impedance. Because you could have like a really high impedance source that you want to get to go low, so whatever's on the other side of that can work more efficiently or work at all. Some things won't accept something that's high impedance, so you could get a very low signal out of it. But to convert that, you can put it in something like a unity gain configuration. With an operational amplifier, you can do this with a transistor as well, as what the emitter follower would be, not the common emitter amplifier, but the emitter follower would give you that kind of thing as well. And what that will do is it won't amplify your signal because you don't want to, but it will change the Z factor, the impedance, to make the amplifier more efficient. Oh, there's some soldering tips a little bit in here. That's kind of cool. Some symbology. So you get all your electronic symbology here. So all in all, I think this is it's a pretty great book. It goes through a lot. Like I said, it's pretty simple, but I think it's all you need. A good introduction, a very good introduction to electronics. I'll be excited to take this course and kind of just have fun a little bit with electronics again, more on the academic side, but it'll come along with building some circuits, so that might be fun too. I'll get to go and use my oscilloscope and do some fun things. I've got some other circuits that I've been working on for a while now that I think since I'm in this class, that'll motivate me to finish them. But yeah, Grob's Basic Electronics. If you're interested, I'm sure you can go online, get a copy. Thrift Books, I believe, is where I got this one. You can find them on discount. Add it to the shelf. Get started. If you have any more questions about electronics, I'd be happy to help you and answer them for you. Have a good one.